All right, AP Physics 2 students, let's talk some magnetism. Where do magnetic fields come from? Well, they come from the movement of charges. Now, this could be an individual charge or, like in a wire, a whole group of charges moving together. So the magnetic field will produce circular loops around the moving charge. In a wire, it'll produce a series of magnetic loops that are all the same strength. We're going to use our right-hand rule to figure out the direction of the magnetic field. So like if this is my wire and the current is going up in the wire, I take my right hand, I point my thumb in the direction of the current, and I curl my fingers around, and so the magnetic field will circulate around like this in this direction. If the wire is coming towards you, then you take your right hand, put your thumb in the direction of the current, and it would curl around for you this direction. To figure out the strength of the magnetic field, here's our equation. Magnetic field strength B is mu naught over 2 pi, which is a constant. Mu naught is on our equation sheet. It's 4 pi 10 to the negative 7th Tesla meters per amp, or mu naught over 2 pi, which is the whole thing. You divide 2 pi into that, and you end up with 2 times 10 to the negative 7th Tesla meter per amp. I, of course, is the current strength, and R is the distance away from the wire. So the farther away we get from the wire, the weaker the magnetic field strength gets. It's inversely related. Remember, since this is by nature a three-dimensional phenomenon, we have trouble drawing this on a two-dimensional sheet of paper. So we use X's to represent arrows that are going away or into the paper, and we represent dots for arrows pointing toward or up out of the paper. If we have a straight wire in the plane of the page, it'll produce a magnetic field that enters the page on one side and exits the page on the other side. So if you take your your right thumb and you point it in the direction of the magnetic field, the way I'm looking at it, it's going to go around like this. It's going to go into the page on this side. It's going to come out of the page on this side. So X's and dots. If we have a loop of wire with a current in it, so if the current's going around this loop counterclockwise, we'll still use the right-hand rule that we could use before. If you stick your thumb in the direction of the current, you can curl your fingers around, and you can follow that current all the way around the loop. And when you do, you'll find that the magnetic field points the same direction everywhere inside that loop. And it turns out it makes a uniform magnetic field, pointing in one direction, and the same strength if we have enough loops. So in this particular case, notice the finger of the disembodied hand of science are pointing out of the page on the inside of the loop. So we have dots on the inside. It should cover up all of it. And then we have X's around the outside of the loop. What if we have multiple loops on top of loops? Well, then that magnetic field strength builds up, and we have what's called a solenoid. And we have a very strong, uniform magnetic field down the center. This is how we produce a uniform in direction and strength magnetic field, is with a bunch of coils called a solenoid. The magnetic field for a solenoid, there's a couple of ways you can figure it out. So there is an actual new right-hand rule if you wish. You can either do it by letting your thumb go around the direction of the current and see which way your fingers point, or you can curl your fingers in the solenoid rule around the coil in the direction that the current is going around the coil, and your thumb will point in the direction the magnetic field is pointing out the center. So if we see that right here, the current is coming around the top and over, so the fingers come over the top and the thumb points to the right. This particular one's a little hard to see. Hope you can see it in the video. The current is coming over the top and down in front, over the top, down in front. So if you take your fingers and curl it around that direction, it shows that the magnetic field is pointing, at least from my perspective, this way. And in this one, the current is going to the right and then up and then over the top in front. If you curl your fingers around, you can see which way the magnetic field points. And this is the solenoid rule for the right-hand rule. Let's talk a little bit about magnets. So here's north and south. Usually red is north, blue is south. These iron filings become magnetized and they line up in the magnetic field. Magnets produce a magnetic field that looks a lot like a solenoid. So if we go back, see this magnetic field? It looks a lot like this magnetic field or this magnetic field. All right? You can see the comparison right here. So So we have the north and south end of a magnet. The magnetic field lines exit out the north and then curl around and enter the south, but they continue through the magnet. They haven't shown them here, but they continue through just like they would for a solenoid. So this would be the north end. This left end would be the north end of the solenoid. And this right side where the magnetic field lines come in, that would be the south end of our solenoid. So it's an electromagnet because it's a magnet produced by current. Magnets are dipoles. They have a north and a south end. You never get just a north, you never get just a south. If you break a magnet in two, it'll actually turn into two smaller magnets. And this is because the magnetic field lines always come in a loop. So if you break it in two, so if I broke this in two, I just have a small loop for this side and a small loop for this side. In a solenoid, we see that there's current, moving charge. Where's the current or the moving charge for a magnet? Well, a magnet is made up of atoms, and those atoms have protons and electrons. Now, primarily the electrons are responsible for our magnetic fields in materials like an iron magnet. The little electrons are actually tiny little dipoles. They're little tiny magnets. So they produce a magnetic field. Plus, they're moving around. They don't actually go in a circle, I know. But they're moving around the nucleus, and that movement of charge also produces a magnetic field. So we have both effects producing a magnetic field for an atom itself. There's several different types of magnetism in materials. The most famous is ferromagnetism. It's when, well, in iron, but also in nickel and cobalt you can get it. It is a material where it has multiple electrons that are unpaired. Remember from chemistry that the shells fill up with an up spin electron and then a down spin electron, then an up spin, then a down spin. But in iron in particular, we get 1, 2, 3 of these in a row that are all spin up. They all have their little magnetic fields all pointing in the same direction. Now what this tends to do is that they naturally align, and so portions of the material will line up into what we call domains, where segments of the material of the iron will have a magnetic field pointing one direction. Now normally you have a jumble of these magnetic domains, and so as a whole the object will not be a magnet. But if you put it in an external magnetic field, these domains tend to start lining up. And if you have a strong magnetic field, they'll line up and they'll end up making a permanent magnet. So if you wrap a wire around, it's like an iron nail, send current through it, let it sit there for a little while, and then take it off, that iron nail will be magnetized and it will be able to pick up paperclip. Now there are other types. Paramagnetism is when you have one unpaired electron, and so they don't make these domains, but if you put them in an external magnetic field, they'll align temporarily and they will be attracted. So you get a weak alignment and a weak attraction in paramagnetism when you have a single unpaired electron. When you have no unpaired electrons, you have what's called diamagnetism, and that's the electrons moving around will produce a magnetic field that's weak, but in the opposite direction. They'll actually repel. And so this is what we get when we have a superconductor. Superconductors are what we call perfect diamagnets. They'll produce a magnetic field in the exact opposite direction and will cancel out the electric field inside themselves. A dipole in a magnetic field. Now a dipole is just a magnet. It's got a north end and a south end, right? So it has a north and a south end. If you put it in a magnetic field, the north end is going to get a magnetic force in one direction, and the south end will get a force in the opposite direction. These forces will be equal and opposite, so it won't translate. But what it will do is rotate and align with the magnetic field. This is what a compass does. The north end will point in the direction of the magnetic field. Let's look at a few examples. So in this example, we have a table that has a wire pointing straight up through it with current going through it. We have some compasses laid around on the table around the wire. Which way will each compass point? Now remember, the compass points in the direction of the magnetic field. So if you curl your finger around the wire, they should point in this direction. The figure shows a current and a long wire. Sketch the direction of the magnetic field around the wire. All right, so I have the current going to the right, and so it should be coming out of the page above and into the page below. So I should get dots above and X's below. Excellent. In this one, we have a current carrying wire designated by an X. So the current is going into the page. And it wants you to draw arrows to represent the magnetic field, but also make the arrows the right length in comparison to each other. So, let's see, into the page, so that would be clockwise, and A is closest, so it should have the largest magnetic field. And there we go. A is to the right because we're going around clockwise, C is to the left, and B is up, but A is the biggest and B is the smallest because of our distance away. In this particular problem, we have a wire with two compasses. They're all lined up, pointing in the same direction as shown. One compass, the one on the right, is below the wire. One compass is on top of the wire on the left. So then we put current through the wire, and we want to know which way these compasses will turn. Right? So the current is to the right, then the magnetic field will go under and up underneath the wire, and then over and down above the wire. So we should get something that looks like this. The magnetic field will go under and up and around the top over to the bottom of the page. All right, magnetic forces on moving charges. Our equation for that is the magnetic force equals QVB sine theta. Okay, Q is the charge, V is the velocity of the charge's movement, B is the magnetic field that the charge is moving through, and this sine theta is the angle between the velocity and the magnetic field. So if the magnetic field is up and the velocity is this way, then we have a 90-degree angle. However, if the magnetic field is up and the velocity is up, then the angle between them is 0, and the sine of 0 is 0. So, a couple of things to keep in mind. The charges have to be moving to produce a force. If the velocity is 0, there's no force. So a charge sitting in a magnetic field receives no force unless it's moving. If the charge is moving parallel to the field, or anti-parallel in the opposite direction of the field, it will not receive a force either. If it's moving at an angle to the magnetic field, then we get a force, but that force is at a right angle to both of those. So we have a right-hand rule for this force. Here's a picture of it. Here's the description. The magnetic field lines will be your fingers. Your fingers point in the direction of the magnetic field. Your thumb points in the direction of the velocity, and your palm will point in the direction of the force. So you end up with 3 perpendicular axes. If the charge is negative, you either do the right-hand rule and the force is in the opposite direction, or you do the left-hand rule and the left hand will tell you the direction of the forces on a negative charge. Right hand, positive charges. So here's 3 practice. We have 3 figures down here. We have magnetic fields as shown, and then we have moving charges. The blue arrow represents the velocity. Pause the video, see if you can figure out the direction of the force on each one of these, and then start the video back up. Did you get these answers? The positive charge here gets a force down, negative charge to the left, and so forth. A couple of things over here. The force on this proton is directed out of the page because the magnetic field is up and the thumb points to the right, so the palm pushes or points upward out of the page. And then the bottom one, the negative charge, you use the left-hand rule, but it's moving up in the direction of the magnetic field. So your hand is pointed up and your thumb is pointed up. There's no angle in between these two, so there's no force on this negative charge down here. Okay, when these charges are moving through a magnetic field, since the force is perpendicular to the velocity, that's not going to speed the charge up or slow it down. What it produces is circular motion. In fact, uniform circular motion if it doesn't lose any energy. So the magnetic force equals, so that's mv squared over r from mechanics, or that's QVB sine theta, and in this case I have a 90-degree angle, equals mv squared over r. So that sine of 90 turns out to be 1, and we end up with r equals mv over qb. Now, this shows up on the test every year, so make sure you know how to get this. And sometimes they ask you for like the mass to charge ratio. or the charge to mass ratio, or the momentum of the object. Okay, so momentum is just mv, solve it for mv, or solve it for m over q if that's what you're looking for. All right, we also have wires that carry these moving charges. So there can be forces on wires because all the charges are collected together in a wire. So our equation for that, the force on a current carrying wire, is ILB sine theta. I is the current in the wire in amps. L is the length of the wire that's embedded in the field. So if the wire passes through the boundaries of the field, you only use the part where the current and the magnetic field are together. And then B is magnetic field, and of course this is the angle between the current and the magnetic field. Now, there must be current. So if I have a wire that's just sitting in a magnetic field and there's no current in it, no magnetic field. Currents that are parallel to the magnetic field will not produce a force, just like a charge moving parallel to the field will not produce a force. And we have another right-hand rule for this one. It's almost the same. Your fingers are the magnetic field. Your thumb, instead of being the velocity of a positive charge, it's the direction of the current. And then your palm again is the force, or the direction of the force would point. So here's a couple examples. I have two figures here, one where the magnetic field is pointing out, one where the magnetic field is pointing in, and I have several currents. Can you draw the direction of the force on each of these currents? Ready, set, go. Pause the video. Did you get these answers? If so, congratulations, you're doing great. If not, go back, look at the right-hand rule again, and practice some more. Okay, what if we have two wires that are near each other, both with a current through them? So I have a red wire and an orange wire here, and they both have current in one direction. So the red wire is going to produce a magnetic field that the orange wire will be in. So the orange wire will receive a force from the red magnetic field, and the red wire will receive a force from the orange magnetic field. So it's going to look a little something like this. So in this case, I have the black wire below, and I've drawn the black magnetic field, and then the red wire is above. So the red wire that's above with a current to the right, magnetic field out of the page, and so the force will be down. Okay? Now we could redo the whole thing for the bottom wire, or we could just realize that, hey, for every force, there's an equal but opposite direction force. So if the red wire gets pulled down, the black wire will be pushed up, equal and opposite third law of forces. It's time to review just a bit. Electric fields are not the same as magnetic fields. They're different. They behave differently. So make sure you understand the differences. Right here in picture number 1, I have a charge that's sitting still. It's a positive charge. It will receive a force to the right. Because remember, in electric fields, you get a force in the direction of the field for positives or opposite the direction of the field for negatives. That's it. So this charge in picture number 1 will accelerate to the right from rest in a straight line. Now, if it has a velocity, say upward, as the picture 2 shows, then it still gets a force to the right because positives get a force in the direction of the field, negatives get a force in the opposite direction of the electric field. So this is positive, so it still gets a force to the right, but it's moving upward. So it's going to be just like a baseball in the Earth's gravitational field. It's going to follow a parabolic arc. Now remember, if we have negative charges, the forces will be in the opposite direction. What about magnetic fields? Okay, here we have a magnetic field into the page, and we have a charge sitting there. It receives no force because it has to be moving, Q, V, B. So no V, no force. On the right, in picture number 4, we have the charge moving upward with a velocity. So it's moving upward, the magnetic field is into the page, and so it will receive a force to the left. And it will move in a circle instead of a parabola, because as it moves upward and turns to the left, the force changes direction, right? So these two fields, you have to know the difference because they will test it every year to make sure you know the difference between electric field and magnetic field behavior. And remember, in a magnetic field, use the left-hand rule for negative charges. So let's practice a little bit. This is a magnetic field. I have a particle moving to the right through this magnetic field, and the particle could be a neutron, a proton, or an electron. So I'd like for you to sketch the path of each one as it goes through. Assume that they all start with the same exact velocity, so sketch the paths proportionally correct. So stop the video and see if you can do that. All right, a neutron, since it has no charge, will go straight through the field and nothing happens. A proton follows the right-hand rule for a magnetic field. It's moving to the right, the magnetic field is into the page, and so the force will be up, and so the proton will curve upward. The electron, negative, follows the left-hand rule. Magnetic field is into the page, it's moving to the right, so it gets pushed down. So why did I draw the electron with a tighter curve? Well, if they're going the same velocity, then the electron has less mass, and so it'll have the same force because they have the same charge as a proton, but it has less mass, so it'll have greater acceleration and a tighter radius. What if we have more than one magnetic field at the same time? So like in this problem, I have a wire that's upward with a current and a wire to the right with a current, and I've got this point P sitting here. How do we handle something like that? Well, just use your equation for the magnetic field around a wire for this wire, figure out what that magnetic field strength is for point P, and then repeat for this one, and then decide whether they're in the same direction or the opposite direction. All right, so mu naught over 2 pi I over r, solve that equation twice and decide what the directions are. So let's see if they add up or whether they subtract from each other. So this current is up, so the magnetic field from that one should be into the page and X, and the 2 amp one down below is to the right, and so it's out of the page. So they will fight each other. So one will be positive and negative, so make sure you add them up as vectors. Okay, what if we have a more conceptual one? So in this particular one, we have 4 different wires in a square arrangement. This wire has a current coming out, as does this one, and the 2 bottom ones have a current going in. And there's a point P in the center of this square arrangement. What is the direction of the net magnetic field at point P? All right, so pause the video and see if you can figure this out. There will be 4 separate magnetic fields that you'll have to sum up as vectors. All right, now I color-coded them to help out just a little bit. So I have the red one will produce a counterclockwise magnetic field going around. So at point P, it's up and to the right. And then this blue one is into the page, so it'll also be clockwise. It'll be clockwise instead of counterclockwise. It'll be clockwise. And so it's going to produce a magnetic field also up and to the right. This green one is out of the page, so counterclockwise. And so it's going to produce a magnetic field circulating around counterclockwise down and to the right. And the purple one is into the page, which is clockwise, and so it will produce one down and to the right. These 2 up and to the right, these 2 down and to the right, and that adds up to a net magnetic field to the right. We're almost done, gang. Let's put this to the nitty-gritty test and see if we can put it all together. So in this particular question, we have a perpendicular electric and magnetic field. We start with a positive charge that's launched between these 2 capacitors. It asks some questions about the electric field between the plates and what the force is and the acceleration is on the charge that's moving between. And then it says we put a magnetic field between these plates to cause the charge to not curve but go straight. So we want to know what direction of the magnetic field will be required to make that happen and derive an equation for what that magnetic field strength will be. And then, once we have that, keep everything else the same that we already have, that we just calculated, and then make these changes. Velocity is doubled. What will that change? If we double the particle's mass, what will that change? And if we change the sign of the particle, what will that change? So I want you to pause the video, take the time to work through this one, and then I'll work it out for you on paper. All right, let's see how you did. So we have a positive charge right here. It's injected at a velocity of v. What is the direction of the strength of the electric field? All right, so this is the positive side of the battery, so that makes this the positive side of the capacitor up here. That makes this side the negative side. And so that means our electric field will be pointing straight down. So there's our electric field, downward. Well, how big is that electric field? Well, actually really easy to figure out. So for part A, the electric field equals delta V over D. And in our case, the distance is D, and the delta V is EMF of the battery. So EMF divided by D, that's our electric field strength, and it is downward. Part B asks, what is the force and acceleration of the charge between the plates? So the force equals MA, and that's an electric force. So the electric force equals EQ, and our electric field is EMF divided by D, and our charge is Q. So there we go. EMF Q over D. To find our acceleration, we just set that equal to MA. So we got EMF Q over D, which is our electric force, equals MA, and the mass is M. So our acceleration is just going to be EMF Q over D with an M in the denominator as well. So that will be the acceleration of the charge as it moves through the plates due to the electric field. Okay, now we're going to put a magnetic field in between the plates so that this charge goes through in a straight line. Now, in order for that to happen, here's the charge. We already know it's getting an electric force downward, which is EMF Q over D. We need a force upward to cancel that out. It has to be equal and opposite. So we need a magnetic force up. All right, so we need a magnetic force up. So I'm going to use my right-hand rule. It's moving to the right. Magnetic force needs to be up. So my magnetic field lines have to point inward. So magnetic field will be into the page. So B field into page. Right now, derive an expression for the magnetic field strength. Well, we're almost there already. The electric force has to equal the magnetic force in order for them to cancel and for it to go straight through. So the electric force we already know is going to be, where is it here? EMF Q divided by D, and that has to equal QVB. And so the Q cancels out, and so I'm left with, for the magnetic force, the magnetic field, is EMF divided by D divided by V. There we go. Now it says, keeping everything else the same, what happens when the velocity of the charge is doubled? All right, so E. If we double the velocity, so twice the velocity, well, does that change the electric force, which is EMF Q over D? And the answer is no. Does that change the magnetic force, which is QVB? And the answer is yes. If we double the velocity, we'll double the magnetic force, which means the magnetic force is now twice as big as the electric force, and so the charge, as it moves to the right, would curve upward in a path something like this. How about F? What if we double the mass, twice the mass? All right, so again, electric force is EMF Q over D, no mass. How about magnetic force, QVB? No mass, so there is no change. Okay, nothing changes. It just travels straight through as before. How about G? The sign of the charge is changed to negative, all right? So now we go from positive Q to negative Q. So what does that do? Well, electric force equals EMF Q over D. If I make that negative, the force changes to the opposite direction. All right, how about this? Magnetic force equals QVB. If I change the charge, then the force changes to the opposite direction. But the magnitudes are not changing, right? So that means what happens is, instead of the electric force being down, now it's up. If the magnetic force was up, now it's down. And they have the same magnitudes, they still cancel, so it travels straight through, and there is no change whatsoever. The mass spectrometer. This is like the mother of all E&M problems. And if you can understand this one, you pretty much understand everything about static electricity and magnetism. So there are three sections in a mass spectrometer. There is a source that produces ions that gets launched into the machine, into this accelerator area. And the accelerator area will have two capacitor plates, one positive, negative, of course, and an electric field, which will accelerate the ion. It shoots through a hole in the one side and then into this velocity selector. This is what we just looked at in the last problem, where we have a crossed electric and magnetic field that cancel the forces out and make the charge move straight through the device at a specific speed. Everything else that's too fast or too slow won't make it through the device because it'll curve either to the right or left and hit the walls here and not make it through the hole. So everything that makes it through this opening will then, we know exactly what its speed is, and once we know this curvature, we can work backwards to find the mass to charge ratio of the ion. Okay, so now let's take a look at the different parts of this in a little more detail. So the ion accelerator area. Remember, there's an electric field between the plates. Remember, it is not radial geometry. So we have to use electric field equals delta V over d, the distance between the plates. And then in this area, we can find the force on the charge and the acceleration of the charge if we wish by, remember, the electric force equals EQ, and that equals MA. And then we could use kinematics to find its velocity on the other end when it launches through the hole. But why would you do that when you can use conservation of energy, which is always the easiest way to solve things? So we have electric potential energy when the charge is over here, and it turns into kinetic energy by the time it exits the hole on the other side. So electric potential energy, VQ, equals 1/2 mv squared kinetic energy. And so you can calculate the velocity that way. So much simpler. In the velocity selector area, we have another capacitor, so we can find another electric field, delta V over d, the distance between the plates. And we know in this area that the electric force and the magnetic force must completely cancel out, so they must be equal. So that means the electric force equals the magnetic force, and from this the Q cancels out, which we saw in the last problem, and so the charge doesn't matter, only the velocity and the electric field and magnetic field strengths. And in the last section, the ion separator. So ions that have a different mass to charge ratio will have a different curvature as they come through here, and so we can detect at different spots on this detector what the diameter or the radius of the path is and figure out what the mass to charge ratio. And in this section we have only magnetic field, so the magnetic field produces uniform circular motion, which is QVB. Sine theta cancels out because we're going to shoot it in at a perpendicular angle, so sine theta is 1, and that equals mv squared over r, our centripetal acceleration. Okay, make sure you understand all the sections of this mass spectrometer because it shows up on the test. At least different parts of it always show up on the test somewhere. Okay, that's magnetism, magnetic fields. And here is a picture of beautiful magnetic fields around the sun. Our next video will be about induction. See you then.